Welcome to the Day 9 solution for the Advent of Code 2022. So today we're crossing a rope bridge in the forest, and we're trying to think about anything else than how likely we are to fall. So we're being given just a single rope to work with, and we're being told that the rope has a knot at either end, the head and the tail of the rope, and the rope stretches a little bit, but not too much. So if the rope stretches more than a certain amount, the tail is pulled towards the head. So we're being given this pointer to Planck lengths. So this is a really interesting bit of physics, but you don't have to understand it. But if you're interested, certainly go and have a look. So we're being told that the head and tail have to be fairly close together. So it's fine for head and tail to be right on top of each other, for them to be right next to each other, or for them to be diagonally one apart. So one along, one up, or any combination of. And then we're being told that if the head moves too far away, the tail follows. So in this example, the head moves one space to the right. That will put them 2 spaces apart, so the tail follows. So that's our problem today, is just we're being given a series of moves for the heads, and we're being asked to find how many unique positions the tail moves to. So I'm not going to jump to code straight away. I'm going to jump to a diagram, and we're going to have a chat about how this can be set up as a vector problem, because that's going to make this much easier to solve. This is a quick drawing of the grid we're working on. So starting with our head and tail at the origin of the grid, and we're going to say that each point on our grid is exactly 1 unit apart, so horizontally and vertically, and then the diagonal distance between 2 points is just given by Pythagoras. So this looks like a triangle here, so we can say 1 squared plus 1 squared, square root it, that's around 1.4, which will be the hypotenuse of our triangle, and that's the diagonal distance between 2 points. So that's going to be useful when we come to do the vector calculations. But for now, let's think about what happens when the head and tail move around. So if the head moves 1 position right, that's fine, they're still 1 unit apart. If the head moves a second time to the right, then the tail has to follow to catch up. So let's look at the vector here. So this would be a vector of 2 on the x and 0 on the y. So we're saying move 2 units to the right and no units up for the head. So then the movement for the tail needs to be going in that same direction, but only moving to catch up, not moving to get on top. So we want to move to here, not to here. So the vectors of that point would be 1, 0. So let's get another arrow in here. One, 0, sorry. And if we think about what happens when the head and the tail move slightly differently, so let's pick another point in our grid. So we'll take the head here, second one, and another tail. So start with them in the same position. Head moves across 1, that's fine. Head moves down 1, that's still fine. Head moves down a second time, not fine. So starting from here, going down to here, the movement would be +1 on the x-axis, and then -2 on the y-axis. So we've moved across and down for the head. So then we want to work out where we would move to for the tail. So the position we want to move to is here, and the vector for that movement would be 1 minus 1. So the trick we can see in both cases here is dividing out by the size of the movement. So when we move along 2 and 0, we can divide out that 2 by itself to give us the 1. And then for the movement of 1 along minus 2 down, we can say, okay, well, 1 is just allowed, 1 divided by 1 is just 1. But then to figure out the 2 movement, we can take the -2 and divide it by the absolute value of 2, so positive 2, and that will give us the -1. So we have a simple rule here, and you'll get to see this again when we write the code, that tells us where we should move the tail to as a vector based on the difference in position between the tail and the head. So that's going to simplify the code a whole lot, rather than having to work out their relative positions and figure out to move each time. So we're ready to start coding. Let's jump into it. This is our input, so we get instructions that say move down by 2, up by 1, down by 2. So we could think about this as move down by 2 positions, but because of the way we set up the problem, it makes more sense to just do it as a move down, then move down, then move up, then move down, then move down. So read it one move at a time, and then keep the tail up to date as the head moves. So I've started by loading that input. So I've split up on space for each line. The first thing in the line is the direction to move. Second thing is the number of times to repeat that move. So let's keep track of all the possible moves. So we'll have a mutable hash map, which maps from a move to a vector to move by. Then we can put all the moves into there. I'm not going to make you watch that, so I will just jump ahead and pop that in. There they are. So up is defined as 0 along 1 up, down as 0 along 1 down, and so on. So we're going to need our starting positions. So the head position starts at 0, 0, and so does the tail. They start on top of each other. And then we're going to want to keep track of all the positions we visited along the way. So we can do that with a hash set of i32, i32, so a hash set of positions. And then we can run through all of our moves. And we'll have each time a direction to move and a number of times to repeat that move. And then we can do this thing the number of times we've been told to. So for don't care about the variable, 0 up to num, which is our number of moves. That should be in. Then we can think about how we actually implement those moves. So if we're being told to move, say, down, like we are first, by 1, we need to grab the down move, which we can do by indexing into the move definitions. So let's do that first. So move def, get, direction, that's a string, and unwrap it because we think it'll be there. So that tells us how much to move by. We then need to combine that with the current head position. So we want to do a vector addition, but you can't just add tuples and have it know you mean that element-wise. So let's define an add function. So take the first vector and a second vector, reference to i32, i32, and that will return the resulting position, so i32, i32. That's pretty straightforward to define, just first.0 plus second.0, and then first.1 plus second.1. So then we can use that to update our h position. And that will need to be a reference. There we go. So that moves our head. Then we need to work out whether we need to move the tail or not. So we need to know how far apart the head and tail are. So let's define a distance function. So that's going to be similar to what we mentioned while we were looking at the diagram. And that will return a floating point. So first thing to do is to calculate the horizontal distance and square it. So let's take first.0 minus second.0 as a 64-bit floating point number, and then compute the power of that to 2. So we'll square the distance between first and second x coordinate. Then we want to do the same for the y and sum those. So that'll be first.1, second.1. So that's the sum of our distances, and then we want to return the square root of that. Not a semicolon. Cool. So we know from the diagram that the distance between 2 points diagonally is around 1.4. So anything more than 1.4 is going to be a move that we have to make on the tail. So if the distance between the head position and the tail position is more than 1.5, we'll just do that to be safe, then we know that we have to make a move of the tail to catch up with the head. So we need to be able to then compute what move we make between the tail and the head's positions. So let's define another function for that. That's going to take a similar input of 2 vectors. And this time it'll return a vector as well. Grab that. Okay, so first we want to work out the actual distances between our 2 points. So the x distance is hpos. Let's name these hpos and tpos. And then we can calculate our y in the same way, which is the distance between the second coordinates. Then we need to normalize. So anything that's larger than 1 needs to be normalized back to 1 so that we don't move onto the same position as the head. So we can do that by saying if x is not 0, then x can be divided and reassigned by the absolute value of x. And we can do the same thing for y. So if y is not 0, then we replace y with y divided by its absolute value. And then we can return the pair xy. That's the move we want to make. So exactly the same as our diagram. Let's do that. So the t movement is defined by the move between hpos and tpos, which is a reference. And then we can apply that using our add function. So tpos gets updated to be the add of tpos and the t move, which is also a reference. And then finally, regardless of whether we update the distance or not, we're just going to track the visited positions. So we can make that slightly more efficient there, but let's just get this working first. So that should be it. We move the head every time we're told to. Every time the distance between the tail and the head gets to be too much, we move the tail to catch up. And then we track all the positions our tail visited. And that's the thing we're trying to get hold of. So if we print this out, tail positions visited. Visited, there we go. And that is just visited.length. So because it's a set, any positions we visit more than once will get collapsed. So we should get the exact number of positions we actually visited with the tail there. Let's give that a run and see if we're looking about right. Let's kick that off with cargo run. And it's saying 6,266. So that seems pretty reasonable. There's 1,000 lines in the file, and we're being asked to make more than one move in most cases. So it seems fairly reasonable that 6,000 is about the number of places that the tail visited. Let's pop that in and see if that's right. So is it? Excellent. We got part 1. So on to part 2 then. Part 2 is asking us to deal with 10 knots instead of 2. So now the head knot pulls knot 1 pulls knot 2, and so on. So it's the same set of rules as part 1, but we've got to deal with multiple knots pulling each other. So if we come down, the first example is a little bit cramped. Let's have a look at the second one. So we can see starting with the head here, all 10 knots are stacked. So then as we start to move the head right, knots 1, 2, 3, 4, and 5 are pulled with it. Knots 6, 7, 8, and 9 are still stacked under 5. So very much the same idea. We should be really careful about comparing pairwise back down through our knots as we move the head around. So let's jump into that. The first thing we'll need is a way to represent our rope. So let's do that as a vector of positions, of knots. And we know we have 10 of those. Let's initialize that so that all the knots are at position 0. And we'll push in origin, 0, 0. Then we want to move all of those knots, so that can be the same logic as before. Certainly to start with. So we'll move through all of our moves, repeat each move the number of times we're asked to. Now there's no head anymore, there's just the first knot in the rope, which is our head. So that'll be rope, get the first element, and unwrap it. And that gets assigned back to the rope 0. So that's that dealt with. Then for the tail, we don't have a tail, we just have the last element in the rope. So that'll be rope get index 9 and copy, because that's a reference. Then for each distance, we're having the head pull not 1, pull not 2. So we want to consider these pairwise. And notice we're not going to run all the way up to index 10 here, because we're going to want to access position 0, which is the head, position 1, to compare the first two. And that's the same all the way up. So for the last thing we want to compare, that'll be not 9 and 10, which are indexes 8 and 9. So the highest we want I to go up to is 8. So we no longer have a head and tail for the pairs. So let's think of this as like a leader knot and a follower knot. So we'll do let lpos for leader position is rope.get at I. And then for the follower position, that is rope get I plus 1 and unwrap. So then we can replace our head and tail variables here, and it does matter which way around these are. So leader is the head, and the follower is the tail. So let's fill those in. And then we'll have that be the follower movement, and then we can update that directly into our rope. So that'll be rope at I plus 1. So that should be the logic we want. The only thing we've got to be careful about here is we're currently still pushing to visited, which we've already used. Let's clear that. So drop everything from it, and then we can print out our result, which is going to be the number of things that the tail has visited, or number of positions the tail has visited. For a second time, and that will be our visited.len. Let's check that. Again, we'll kick that off with cargo run. And it's saying the tail only moved 3 times. That does not sound right. Let's check that code. So what have we missed? Others jumping out at me here. So this is underlined, saying it's mutable, but both of the variables we should be working here are not mutable. So that shouldn't be referring to tpos, should be referring to fpos. So dangers of copy pasting. Let's see if that makes a difference. Okay, how about this time? So 2,369. So that seems about right. So we expect a lot less movement than the first time, because the head has to move a lot further to pull the tail. So intuitively that seems about right. Let's check if it's the right answer. So is it right? It is. Fantastic. Hopefully that solution made sense today. It's much easier once you've figured out how the vector logic works. So if that bit didn't make sense, try drawing it out or comment, and I'll see if I can come up with a better explanation or answer any questions. So this move function really is the key, and it's this bit that's worth drawing out. So taking the different positions the head and tail can take around each other, and figuring out exactly what this function will give you to see that it does pull the tail in the right direction. But otherwise, I will see you tomorrow.